class. How are we all? Yeah? Good morning so far? Yes, good. For my Danish friends sitting over in the corner, I heard a joke about the Scandinavian countries, which clearly doesn't apply here from the interaction already. There's a famous comedian in the UK called Sandy Togsvig. If any of you have come across her, she's a brilliant stand-up. She hosts QI, a big panel show, and she tells the story of the first time she tried to do stand-up in Scandinavia. It was in Denmark, and she did 20 minutes, and she thought it was her best 20-minute set. And everyone just sat there looking at her. No laughter, nothing. And at the end, she thought she'd done a terrible job. And she said, "Oh God, I'm sorry, I hope that was okay," at the end. And the organizer said, "No, it was fantastic. We all loved it. We were just too polite to interrupt." Very different in this part of the world. So morning, I'm James, as the introduction said. So I'm going to be talking today about this stuff. So team topologies, software architecture, complexity science. Really, this is a sort of summary of what I've learned over the last, I guess 10 years since I was involved in the early days of microservices. So when Martin Fowler and myself wrote the, definition of microservices back in 2014, or published then, we said this: we cannot say there is a formal definition of the microservices architectural style. But we went on to say that what we can say is that there is a set of characteristics of microservices that we are seeing around the place, that we are seeing successful organizations using across the world. So the Netflixes of the world, the Guardian newspapers, a lot of investment banks and front offices and things. We're using or building systems that seem to have a common set of properties. And these are those properties that we talked about. I'm not going to go through these in detail, but to point out that my journey over the last 10 years has sort of seen me trying to understand if there's anything deeper than these, if there's anything that lays behind, if you like, why microservices has arguably become the sort of predominant architectural style. And I'm going to focus on, or really my journey is sort of focused on the idea of decentralization, the idea of sort of pushing things out to the boundaries, decision-making to the point where people know the most, as opposed to going up through hierarchies to where people know the least, to ivory towers, if you like. So componentization via services, splitting things into smaller things. Taking a big problem, if you've got a big problem, how do you solve it? You break it up into smaller parts and solve the smaller problems. So componentization via services. And then the idea of organizing around product teams or building products, long-lived products, building software that's never done, as opposed to short-lived project teams where I might be flipping between 50% on this and 25% on that and 25% on that. And so over the years, I've been thinking, is there anything behind this, anything deeper, anything that we can sort of seize on as a sort of underlying set of principles? And I think there are. I'm going to be talking about some of those in a minute. But the first thing I'm going to be talking about is team topologies, because it has direct impact, I think, on these characteristics. So team topologies and complexity science, or team topologies and complexity. Now, the great thing about team topologies is, for me, it provides a ubiquitous language for us to talk about organizational design and team structures. It allows us to communicate in a domain-driven design sense of ubiquitous language amongst each other, between ourselves. And I'll illustrate a little bit of that with a story. So I was at a workshop. It's a tough life I have. It was in the Caribbean, right? So it was in a little island called Anguilla. And there was someone from Amazon Web Services there. And they said this: as we scale at Amazon, the easier it is for us to get bigger. So the bigger we get, the easier it is for us to scale further. The more teams we add, the more products that we build, the easier it is for us to build more products and add more teams. And that sort of flies in the face, pretty much, of kind of received wisdom in terms of scaling our delivery teams, right? Usually you expect to hit a limit where you're scaling. In fact, microservices, in a sense, was an attempt to solve this problem. By breaking things up into smaller parts, we were able to scale more people, more teams around the individual services to go faster, to optimize for flow. For me, the goal, essentially, of team topologies or successful organizational design, the goal of what we're doing when we're designing teams and therefore software architectures, if you like, to to deliver their software, is to optimize for flow of value to our customers. Right? It's to optimize for the flow of stuff from idea, from customer, through into production. Whether that's to make more money, whether that's to save lives, or whatever it is. The goal of design is to optimize the flow of value. And really, all else, I think, is subordinate to that. That's me, by the way. Daniel Terhorst North puts it really beautifully. He says, the goal of a team should be to safely and sustainably reduce the lead time to thank you. Right, to reduce the lead time to someone, it's not in production, but to someone saying thank you for that. Which brings me to the question, what is value? If we're trying to deliver value somewhere, what is value? Well, in my mind, value could be anything. It's stuff. It could be information. It could be knowledge. It could be features into a software system. But similarly, it could be physical stuff. It could be a car that's delivering value when you buy it. It could be oranges being shipped from one place to another so I can eat the orange. Essentially, it's basically the flow of stuff through progressively more value-enhancing processes until it gets to your door or to your laptop, to your browser, or whatever it is. And if you squint, actually physical products like oranges or cars and knowledge work, they're the same sort of thing. Essentially, we go from something that's less valuable through progressively more value-enhancing steps to something that's more valuable. And that can be sold. And that is basically the goal of most organizations, right? We take raw materials and turn them into a thing. The difference with what we do is it's knowledge work, right? So the stuff is invisible. The requirements are written down, but they're kind of ephemeral. They're sort of invisible inventory. So this brings me to the question, which will become relevant later. How long, in general, does stuff take? Now, this is from a 100-year-old plus company. This is a value stream map. If you haven't seen one of these before, this is a map of the value-enhancing steps that stuff goes through. In this case, it's software. So it starts off with business requirements being gathered at this end. All the way down this end, stuff gets deployed into production. I have got a laser. Excellent. Is the laser working? Can't see the laser. I'll point. That sticky note there is someone writing code. All the rest of it is stuff that's accumulated over the years where this organization has added more and more processes, more and more constraints, more and more queues, more and more checklists, more and more people that have to say yes or no. You have these really, really long value streams in most organizations. Which is why I love this book, Team Topologies. And I really hope you've come across this already, and if not, I really strongly suggest you get hold of it. I think it's one of the most important books, I think, that's been written about what we do, along with things like Accelerate or Continuous Delivery, or I have to plug Sam Newman's Building Microservices, but about what we do. It's the canonical reference for how we can talk to each other, as I say, about how teams work. So what do I mean by that? Well, in Team Topologies, they talk about 4 fundamental types of team. The first one is a stream-aligned team, a value stream-aligned team. So a team that's delivering stuff directly to a customer, with direct line of sight to a customer. If you imagine if you're building a website, you might have a value stream-aligned team around search or around catalog, around your basket, say. But essentially direct line of sight. You then have enabling teams. So enabling teams solve the problem of scarce resource. Right? There's not enough InfoSec people out there. There's not enough really good infrastructure engineers. How do we scale this scarce resource? Well, we use them as consultants to the rest of the organizations. Their job is to make the other teams go faster, essentially. Then you have complicated subsystem teams. Sometimes, there are problems that you need lots of context to solve. Yes, we can be full-stack developers. Yes, we can work in vertical slices. Sometimes you just really need to know a lot about risk or a lot about quant-style models and investment banks. Complicated subsystem teams. Then you have platform teams who are building tools that allow the other teams to go faster. And what I like about this model is it acknowledges that there are different types of things you need to solve for in organizational design. Originally, in the microservices characteristics, products over projects, build product teams. This takes that further and says, actually, that's not the only problem that we need to solve. Yes, we need these value stream aligned product teams, but we also need to solve these other problems too. So you get to pick how to solve these problems from this sort of set of patterns in the book, all the research that they've done. And finally, fundamentally, this is about flow. It's about organizing our teams to enable the flow of change, the flow of value to thank you, if you like. I'll touch briefly on software architecture and complexity now. So I'll go back to this quote. The bigger we get, the easier it becomes to get bigger. Dry mouth. Too much coffee. All right. The bigger we get, the easier it becomes to get bigger. Now, this is received wisdom, right? Mythical Man Month. Adding manpower to a late software project makes it later. So, the original research was as you add more people, the communication overhead, the information flow overhead between people on a team, on a program of work, right, at some point becomes greater than the additional capacity gives you in terms of delivery, right? Delivery of value. So you add capacity, at some point that capacity isn't adding any more value because they're having to coordinate so much, right? This is received wisdom. So how is it that AWS claim the bigger we get, the easier it becomes to get bigger? And I think it's about a set of forcing functions that were imposed on AWS's architecture right at the start, or Amazon's architecture right at the start. Pseudo-graph income, and if there are any data scientists, there's only so many points on this because this was the only information publicly available. This is a log graph of revenue versus employee count at Amazon. So what this is showing, essentially, is that as Amazon doubles in size, as they double the number of people they have, they more than double the revenue they're making. Right? This exponent of 1.15, that's saying that exponent means that they're growing in advance of how they should grow. I'll come to the data that shows that in a sec. But Amazon, it appears, from the publicly available information, are making more money than they should. As they add more people, they're making more money than those people should be able to make for them. And why is that? Well, again, it's about the software architecture that they've, over time, implemented, right? And that led to AWS. So if you think back to 2004, whatever it was, these forcing functions that Jeff Bezos imposed around communication via interfaces, we're not going to fertile around with each other's databases or big databases anymore. We're going to build service-aligned teams, not necessarily microservices, but service-oriented architecture, and you must communicate via interfaces. Those interfaces must also be externalizable, right? So if I'm on a team providing an interface to another team at Amazon, I should be able to monetize that. I should be able to sell that elsewhere. This is where a lot of the AWS product suite came from. And finally, limiting team size, limiting coordination overhead, right? Forcing functions that allowed the Amazon software architecture to grow in a particular way over time. So these, I would say, they're not just forcing functions for the software architecture and how that was able to evolve and grow, but also to allow Amazon to improve the flow of value within the organization, to get stuff done more quickly, to get stuff into the hands of people, of customers faster, essentially, forcing functions for flow. So limiting interaction to nearby teams, isolating teams from one another, and scaling by Dunbar's number. When we talk to componentization via services and microservices, what we mean really is we want to create these sort of decoupled teams, decoupled sets of services that are isolated from one another, where the change radius, if you like, the blast radius of change is limited to a single team. And it's cohesive around business value, around business capabilities, as we sort of called out. And that's what Amazon did. They've used these forcing functions to guide the software architecture in a particular direction. Which brings me to the third topic I wanted to cover, complexity science, or complex adaptive systems. So these were, I guess, first researched as a result of research into chaos theory, actually, by a group of physicists from Los Alamos National Laboratory in New Mexico. They started this institute called the Santa Fe Institute, which is in, funnily enough, Santa Fe. And it's the idea behind the Santa Fe Institute is to provide a cross-disciplinary view on complexity, a cross-disciplinary view on things like economics, but also physics and chemistry and biology. And particularly this study of what has become known as complexity science or complex adaptive systems. Here's some fun facts for you. So mice and elephants. So as you scale a mammal, as a mammal gets bigger, as you double the size of a mammal, certain things happen and certain things remain constant. So I don't know if you knew this, but all mammals have about the same number of heartbeats in their lifetime. We have the same number of heartbeats as a mouse and as an elephant. We also have the same blood pressure as a blue whale. That's kind of interesting, isn't it? So what is it that changes? If you've got these constants in, as you scale the size of a biological thing like a mammal, and you've got these constants, blood pressure and number of heartbeats in a lifetime, what changes? And it turns out what changes as you double the size of an animal is the metabolic rate. Metabolic rate slows as you get bigger, right? So as you double the size of a thing, the metabolic rate slows, actually quite significantly. So you only need 75% of the calories if you double the size of a thing than you'd expect. You don't need to eat twice as much food to sustain yourself. And it's because things slow down. The metabolic rate slows. Elephants don't get cancer, really, because their metabolic rate is so slow that their cells, right, the cells don't have enough time to age and pick up all the genetic defects that cause cancer. Right? They exist really, really slowly. Mice exist really, really fast, just going around the place the whole time. So metabolic rate in mammals follows this scaling law with an exponent of 3/4. As you double the size of a mammal, you only need about 75% of the calories. But there are other examples of complexity and complexity science, complex adaptive systems around as well. So organizations are another complex adaptive system. As you double the size of an organization, again, other scaling laws apply. So if you look at, this is data from NASDAQ, as you double the size of an organization in terms of employees, you don't get double the amount of revenue out. What you normally get is, from this data, it was about 75%. There's more data that points to about 85% of the revenue. You should expect, as you double the size of a company, to get about 85% of the revenue. You don't get 100%. Revenue scales with number of employees following a similar scaling law. I've personalized this, can you tell? Or localized it, maybe, that's probably the better word. But as you go from one city to a city approximately double the size, other scaling laws or similar scaling laws apply. So as you double the size of a city, you only have to spend about 85% of the money you think you should on infrastructure. So as you double the size of a city, you only need about 85% of the petrol stations that you think you might need, not 100%. You only need about 85% of the water pipes, of the electricity cables, etc., etc. You don't have to get double the number of these things as you double the size. This is what we refer to as economies of scale. So infrastructure scales with population with this exponent of 0.85. Road length, number of petrol stations, there are number of restaurants, water pipes, etc., etc. So what we've got is a number of different straight lines and graphs, if you like, examples of scaling laws across multiple different types of complex adaptive system, biological life, mammals, companies, and organizations. And whenever we see these straight lines, we should be thinking about why we're seeing straight lines. Are there underlying properties that we're missing? Quantities that do not change when other parameters of the system change, they play a special role in science. This is from a book referenced at the end. There's a bibliography at the end of the talk. But from a book called Scale by Geoffrey West, The Universal Laws of Life and Death in Organisms, Cities, and Companies. And it's a fantastic book. It talks in detail about the mathematical proofs of what I'm sort of talking about during this complexity science part. But as I said, what we're talking about when we see these straight lines, these scaling laws, is the idea of economies of scale. It's what economists call economies of scale. It's what our CFOs say when our CFOs say we're gonna get a bigger office because if we have a bigger office, we're gonna have save economies of scale or whatever. We don't have to spend so much on rent. The bigger the office, if you double the size of an office, you have to spend not double the amount on rent. So economies of scale is when we have this idea of sublinear scaling. On a log-log graph, you see these straight lines. As one number doubles, another number doesn't double. It's less than double, if you like. So revenue, metabolic rate, and infrastructure in cities. I've given you some examples of complex adaptive systems, but what are they? So they have 4 characteristics, essentially. So they're made up of self-similar parts. If you think about a mouse and an elephant, they're made up of the same cells, right? Or they look the same at the fundamental, at the bottom, self-similar parts. They display self-organization. There is no central orchestrator, conductor, telling the cells to build itself into an elephant. It sort of happens, right, according to nature. They are complex, by which I mean the whole is greater than the sum of the parts. So you could cut me up, you could put me in a blender, or any of us. I'd put me in the blender. You put me in the blender, blend me up. There's like a soup, right, of me, James soup. It's not a very nice idea. You couldn't then put that into a James-shaped mold and put it in the oven and get James out again, right? I am a much more complex thing than you would expect from just the sum of the parts, the self-similar parts. And complex adaptive systems, they display emergent behavior. So if you run the same system or simulation or experiment twice with a complex adaptive system, you probably get different outcomes, different answers. And you can think about this in the context of our teams. When we're building software, if I go on holiday for a month, the fact that I've not been around for a month means that the software is going to go in a different direction. Right? The lines of code that you write in my absence are going to be different lines of code. They might be similar, but they're going to be different. Right? When you run the same set of situations through twice, you get different outcomes, emergent behavior. And fundamentally, mathematically, actually, complex adaptive systems can be simplified to 3 simple principles. The first one is the idea of space-filling networks, fractal networks. In this case, I'm talking about hierarchies, and I'll be talking about hierarchies in the context of team topologies and software architecture for a little while now. Essentially, a hierarchies like your blood vessels, the circulatory system, or the network cables, or the water pipes in a city, so hierarchical networks. Then we have what my people team in work call us consultants at Thoughtworks invariant terminating units. It's better than the alternative, which was meat bags. That's what we used to be called. But the idea of cells in biology, invariant terminating units, people in organizations, people consuming information and producing more information, value. And in cities, it's houses and people living in houses. And then finally, some mechanism of optimization, some way of tuning the system. In biology, that's over geological time via feedback from evolution. In cities and in companies, it's feedback from market forces. And just with those 3 simple properties, there are equations and things. There is math exists, that shows you get all these straight lines popping out. They can explain these different scaling laws for metabolic rate, for economies of scale for infrastructure in organizations, in cities, and also for revenue in companies. And as I say, they're everywhere, right? I've given you some examples. Pretty much everything you look at in some form or another is a complex adaptive system, unless it's super, super simple. They can be described with these 3 principles. But the key thing is, if you have a hierarchy, you end up with economies of scale. It is maths. It's inevitable. Hierarchies lead to suboptimum, for some value of optimum, revenue growth. Hierarchies lead to this 85% rather than 100% revenue growth. And also, this kind of scale invariance, I guess, from maths or physics. In Walmart and a convenience store, they're pretty much the same. A mouse and an elephant are the same thing, more or less, barring the differences according to the scaling laws. Which brings me to the next thing I want to talk about, which is stuff slowing down. This is a little bit depressing, so I hope you don't mind. Why does revenue growth slow as size increases? Why do we get this scaling law? Why do we get this graph happening? Why did metabolic rates slow as size increases? It's the same reason, right? Hierarchies. Anytime you have a hierarchical network, from maths, it's maths again. Anytime you have a hierarchical network, you see these scaling laws. And the deeper the hierarchy, the slower things get. The deeper the hierarchy of our circulatory system, the slower the metabolic rate. It's a function just of these three principles. Right? The deeper the hierarchy in an organization, the slower information flows. This leads to the revenue increases being suboptimal. And in cities, the hierarchies, the deeper the hierarchies of water pipes and so on, means you need fewer of them. It's a property of something called the fractal nature of these networks. So, these interesting facts, right? Bigger animals are more efficient. You don't need to eat as much. And so are companies. They're more efficient. You don't need to spend as much on infrastructure. And it's due to this idea of impedance matching in the circulatory system, the depth of the hierarchy and optimizing the hierarchy over time, driven by evolution. Companies are also more efficient. I mean, our CFOs are right. As you double the size, you do get economies of scale. But you also develop deeper hierarchies, and you don't get as much revenue out as you might think you get. And also, in terms of biology and companies, they both slow down as they get older. So as we get older, our cells age. As we get older, we have to spend more of our energy repairing our cells rather than growing new ones. That's why my hair's grey. I've got aged, wrinkled skin because I'm the grand old age of now. We have to spend more and more of our calorific intake, the energy we take in, on repairing ourselves, right? And it's the same for companies. So back to this idea of flow. I talked at the start about, the idea of optimizing organizational design or software architectures is to get stuff to our users as optimally as possible. The idea is to get stuff, to the point of saying thank you. So I pointed out this value stream map earlier. I showed an example of a value stream map earlier. And if you think about value stream maps, it's essentially a slice through the information flow through your organization. It's a path through the hierarchy, a path through the network in your organization. And the deeper the hierarchy, the longer the value stream map, in essence, the slower things are going to get. Don Reinhartson, the great Don Reinhartson, I've actually met him, so I'm going to say Don. Don Reinhartson wrote this amazing book, Principles of Product Development Flow. He talks about the economics of product development. And in this, he talks about the dangers of queues and the dangers of adding lots of queues into a system. And when we build up these big value stream maps, these big hierarchies, when we have lots of change request boards, we have to go and ask permission to do things, too. Right? What we're doing is we're blocking flow. We're we're impedance mismatching the flow of information. So back onto another topic, corporate metabolism. So as companies scale, what happens is they add more and more processes and hierarchy. A 100-year-old company that's accrued all this sort of scar tissue. Oh, why do we do 8 weeks of regression testing? Well, that's because, 3 years ago on a Friday, accidentally a bug got into production and it took the whole site down. We couldn't sell anything. So now everything has to go through 8 weeks of regression testing. Why do we have to do all this before? Well, because there was a bug got in. And you end up with all these process steps. And over time, these things accrue. The hierarchies deepen and deepen and deepen. You add more constraints. And that's why things slow down. Bigger companies are slower in the same way that elephants are slower. They just are, because of the depth of the hierarchies, because of their age. But we also deliberately do silly stuff. So, a quick sidebar now on another brilliant book I mentioned, I think at the start. So, Accelerate, another one of these sort of canonical works that's been come out in the last few years, based on the original work by the Dora Institute. I can never remember what that stands for, but Nicole Forsgren's the first author on this work. So, Accelerate, if you haven't come across this is original research about why what we do works or doesn't. Right? And in that, they identify a number of key metrics which you can use to essentially gauge organizational health or age, metabolic rate, if you like. How healthy is your organizational architecture? How is your software architecture? How healthy is your ability to get stuff into production? So, fun fact, change request boards predict low organizational performance. And that means they predict lower performance on the market, the stock market, lower revenue. You get lower revenue if you have change request boards. It's a predictor of it. based on the data. So, with these 4 key metrics of mean time to recovery, cycle time, change failure rate, and the number of deploys per unit time, these are the equivalent, if you like, of taking our pulse when we go to our general practitioner, our GP. We're not feeling quite right. What's the first thing they do? Blood pressure, pulse, temperature, maybe your oxygenation levels, etc. They've got a few simple indicators that let them know not what's wrong, but if something's wrong, right? And these are the same thing. These are indicators that let you know maybe something's not quite right here. Maybe we're not performing organizationally as we should. So optimizing these things is a bit like sort of, going to the GP and them giving you some antibiotics or whatever. So, as I say, the great thing about these 4 key metrics is that they're leading indicators, if you like, of organizational health. They're leading indicators of how well the organization is doing. And it's a bit like monitoring heart rate and blood pressure. So we can act to improve our organizational design, the flow of work, and we can see the results by monitoring the 4 key metrics, but only to the limit of the hierarchies that we have in place. There's another thing that happens to organizations. They die. And apparently this is because as we get older, we have to spend more and more of our calorific intake, our energy, on sustaining ourselves, repairing ourselves. Seems like organizations have a similar thing that happens. As organizations get older, they spend less money on the thing that made them great to start with, less money on research and development, less money on product innovation. They move into this state of just having to sustain themselves. They spend money on cost efficiency, cost reductions, just almost like you spend money on just being the company, not on R&D. In the same way that we have to spend all of our energy on just retaining what we have rather than running marathons or something. And they also add more and more processes and constraints as they get older. Add lots and lots of checklists and all these sorts of things. And that leads to the hierarchies growing and growing and growing. More and more middle management. More and more people you have to ask for permission to get things done. And hierarchies, they lead to this slowdown. So hierarchical organizations, they gain economies of scale for infrastructure, but they achieve sublinear growth in revenue. And eventually, hierarchical organizations, the metabolic rate slows to the point that an organization dies. 50% churn every 10 years on the markets, listed companies. The half-life of a listed company is 10.5 years. That's the amount of churn. But there is good news, because there's another type of complex adaptive system that isn't biological and that isn't an organization that seems to have solved this scaling problem, right? Seems to have solved the problem of how to avoid this thing slowing down because of hierarchies. There's another type of scaling law called returns to scale. This is when we double the quantity of one number, log again, we more than double the quantity of the other number. We get more out than we think we should, as opposed to economies of scale when we get less out than we think. And cities exhibit both returns and economies of scale. So for returns to scale, you get greater than expected growth in innovation, wages, professionals, all these socioeconomic things. But for infrastructure, you get this economy of scale. You don't have to build as many roads or petrol stations and so on. Also, walking speed. As you double the size of a city, people actually do walk faster than they should. It's a funny thing. And maybe they cycle faster in the Netherlands, I'm not sure. But up to the limit of how fast your legs will go, people actually walk faster. And the thing is, it's because of these social networks. The socioeconomic factors are driven by social networks, by connections between people, by connections between your close family and friends. Your acquaintances, the people you work with. You get to choose who you want to hang out with in cities, right? You get to build the network you choose out of society. And that's what drives this growth, this superlinear growth, accelerated growth in innovation and all these good things. Also crime and pollution and so on. Social network effects. Social networks are the driver for returns to scale. I want to drive this point home. Hierarchies lead to economies of scale. They lead to less out than you think. And social networks lead to returns to scale, more out than you think. And the interesting thing is, because with social networks, what you can do is you plug bits on the side. As cities grow, you just add another suburb on the side, add another a little bit on the side, a little bit on the side. You can actually tell the health of a city by measuring how crinkly the edges of the city is, the fractal dimension of the city. But with hierarchies, it's much, much harder to actually change those hierarchies. You just add depth, add depth. And as you add depth, things get slower. It's maths. So, to summarize, as cities grow, they gain economies of scale for infrastructure, they gain returns to scale for socioeconomic factors. They don't often die, and effectively you get 115% of the stuff out for 85% of the cost. This is why they are so successful. This is why cities, well, there's an old joke, if you looked at the Earth from space, an old quote, if you looked at the Earth from space, you'd be forgiven for thinking that cities were the predominant life form, and that humans were just the equivalent of their gut biome. They're such a successful organism, if you like, complex adaptive system. So other examples of organizations that scale using these social networks, right, as opposed to hierarchies. I would argue that Thoughtworks has done this over the years, but then you would say, of course you would, you work for Thoughtworks. This is the only sales bit. Thoughtworks, yeah, we're amazing. You could also say that Spotify, the Spotify model, is an example written down of how to try and grow with a structure that's akin to growing social networks. You're growing additional squads and squads and squads, and then you're building just enough hierarchy around those squads, around those teams, to enable effective communication. Valve's employee handbook, which was leaked some time ago, they actually had this diagram in it, which basically is an example of how we want to grow, and they call out social networks as the driver of growth, the driver of them scaling. And then finally, back to Amazon. Bring you back to this graph at the top. Funnily enough, this 1.15, this is the exponent you get when you're driving superlinear returns to scale, based on social networks, fractal social networks, small world fractal networks, they're called. This graph is pointing to the fact that the way Amazon have structured themselves, the way they've built their software architecture over the years, the forcing functions they use, the way their teams are sitting based around, talking to having a direct line of sight to the customers. Customer focus, but isolated from one another. Decoupled, cohesive around business concerns is driving superlinear returns to scale. So as most companies get bigger, it gets harder to get bigger. But as Amazon gets bigger, it seems to get easier to get bigger. I started by talking about team topologies. I can't recommend this book highly enough. They're good friends of mine, acquaintances of mine from the London continuous integration and CD community and DevOps community. They're fantastic at what they do. I can't recommend this highly enough. Take a look at the models, and I'll summarize by saying, my 10-year journey has led me to think, are there these underlying principles behind these characteristics that we identified in 2014 or whatever it is? And I think there are, and I think it's about complexity science. I think it's about these simple properties around social networks, not around building hierarchies. Hierarchies make you go slower, social networks make you go faster. I'll move through this, because I've said it already. So I'll finish up with a bibliography. Thank you very much for coming. The slides will be available, as will the video. And yeah, it's been great to be here. Thanks so much.